Good afternoon, everybody. I'm very pleased to be here. Thanks to the organizer for inviting me. My name is Katrin Altweg. I'm the principal investigator of the Rosina instrument on the Rosetta mission. And what I'm going to show you is, of course, a teamwork of the whole Rosina team. Rosetta, the European spacecraft, went to Comet 67P through Churyumov-Gerasimenko, and you see this comet here as we saw it in 2014 when we arrived. It was quite some surprises. It didn't look as we were imagining it. It's a weird shape. It's almost a duck, and it has a rotation period of something a little bit more than 12 hours when we arrived, and this then decreased over time. The rotation axis of this object is not perpendicular to the ecliptic, it's tilted, and that makes, first of all, diurnal variations because it rotates, and it also makes seasonal variations because it has winter and summer on the comet. Rosetta was following this comet for more than 2 years with varying distances. So the closest we got was 2 kilometers above surface before we then actually landed. Then the distance was 0. But during perihelion we had to retreat due to a lot of dust, which confused the attitude regulation of Rosetta. And we were at 350, 400 kilometers from the comet. The comet has a period of 6.5 years. It has a perihelion of 1.25 AU and an aphelion of 6.5 AU. When we arrived, it was almost at 4 AU. We went with the comet through perihelion, and we left it again at almost 4 AU on the other side of the sun. Our instrument is a mass spectrometer. Actually, it's 2 mass spectrometers and a pressure sensor, and it's designed to measure what comes out here of the comet. Not what you see, that's the dust, and the next talk will be about the dust, but the gas. And the gas comes out because the comet gets heated by the sun and ice is sublimating. So that's our workhorse, DFMS. It's a classical mass spectrometer, magnetic mass spectrometer. It has a very high mass resolution, but if I tell this to the lab people, they just laugh. It has a mass resolution of 9,000, never before flown in space, but of course in the lab you can do much better. The questions we want to answer and which are relevant for astrobiology is, first of all, the origin of this material. Where was it formed? Is it pre-stellar? Is it during collapse? Is it in solar nebula? And how was it modified? Then how pristine are comets? What happened in the last 4.5 giga years since comets were formed? And of course, what is the inventory of organics in a comet? And finally, did comets actually deliver material to the Earth, and if so, how much? Origin of cometoriasis. That was one of the first measurements, and probably you have seen this graph before. It's the d/h in water for several bodies. So we have meteorites here, we have the Earth, the terrestrial value here, the giant planets down here, together with the protosolar value, and then we have comets. And these are all Oort cloud comets, with the exception of Hartley 2. And Hartley 2 it was the first Jupiter family comet which was measured, and it had actually a terrestrial value. So the question was, what is CG doing? It's also a Jupiter family comet, and it turned out that CG is very high in d/h. So what can you learn from this graph? You probably learned that comets are quite diverse in d/h. and that it does not play a role if it's a Jupiter family comet or a Oort cloud comet. They were probably formed over a large region in the solar nebula, radial distance from the Sun, and then their fate was just dynamics, if they ended up in the Oort cloud or if they ended up as a Jupiter family comet in the Kuiper belt. What's more interesting is probably this here. We were able to measure the doubly deuterated water, and the ratio doubly deuterated to singly deuterated is very high. It's 1.8%. If you look in the molecular clouds, you get values which are very similar to what we measured. And there is a paper by Furuya et al. In 2016. He looked at this and he found that if this ratio, so doubly deuterated to singly deuterated versus singly deuterated to normal water is high, then it's unprocessed water from the molecular cloud. For reprocessed water in the solar nebula, this ratio would be 0.25, 1/4. In our case, it's 17. So that means that much of the bulk water of 67P has been formed in the molecular cloud stage, star-forming region, and has survived as ice to the comet. It never sublimated in the solar nebula. We were able to measure xenon. Xenon is a very cool element because it has actually 9 isotopes, 9 stable isotopes, and they are formed by different processes. P process, which forms supernova, which gives you the P process, and that gives you the very light xenon. We didn't see those. They are not abundant enough. Then HEB stars, they give you mostly the intermediate xenon from 128 to 132. And finally, our process, neutron star mergers, give you the very heavy xenon. In addition to these processes, you have an addition to the xenon 129 by radioactive decay of iodine 129, which has a lifetime of 15 million years, roughly. So we could measure 7 out of the 9 xenon isotopes in Churyumov-Gerasimenko, and that brings us to the Earth. The Earth has actually a problem with xenon. In the atmosphere, it has two problems. In the atmosphere, if you normalize it to the sun would be here, then chondrites are here, and that's for the different noble gases, neon, argon, krypton, xenon. So chondrites are here, and the Earth relative to the sun is here. It's parallel to chondrites, but it clearly misses xenon in its atmosphere. And on the other hand, if you look at the xenon isotopes, again, normalized to sun and normalized to xenon 132, so that gives a straight line for the sun, you see the Earth has a mass fractionation. The higher the mass number, the more xenon you have. Now this you can probably explain by loss of xenon from the atmosphere of the Earth. And the explanation is actually that you can ionize xenon much better than the other noble gases, and you lose ionized species much easier from the Earth's atmosphere than neutral species. So that gives you the mass fractionation. Here, this peak was interpreted as coming from iodine 129, and this was actually used to date the mantle formation of the Earth, as people were claiming that this iodine 129 is in the mantle and is outgassing. Now, if we correct for the mass-dependent fractionation, then we get this curve. It's still not solar. Orange is solar. We can correct. We take away the iodine 129. And then it's solar up to 132, but it's depleted in 134 and 136. And that's our Earth's atmosphere. The Earth's mantle is different. So 40 years ago, almost in 1978, Pepin and Finney claimed that there has to be a non-solar component of xenon called U-xenon. U not being uranium, but U standing for the German word Ur, primordial xenon. U-xenon has been looked for in meteorites, in interplanetary dust particles, and so on, has never been found until 67P. So 67P is the blue curve. We have a large error bar here because 128 is not very abundant. We have a peak at 129, then we are more or less solar here, and we are depleted in 134 and 136, exactly as the Earth's atmosphere. So from this, we can conclude if 67P is typical for comets, which we don't know, it's the only sample we have, then you take 22% cometary xenon, 78% chondritic xenon, and you match exactly our Earth's atmosphere. I think that's a nice result, especially as you now can calculate how many comets impacted the Earth. I will come to that later. We have other non-solar isotopic ratios. We were able to measure silicon 3 isotope plot, so it's silicon 29, silicon 30. You see solar would be here in the center. Our value is slightly depleted in both the heavy silicon isotopes. We could measure silicon, it's not volatile, I know that, but we could measure it because early in the mission, solar wind was still hitting the cometary surface and was ejecting silicon from the dust. So it's depleted in both heavy isotopes, and as a check that the instrument works, this is 13CO, which is on mass 29, and for carbon, it's exactly solar, within error bars, of course. So it's the same mass, we have both peaks, and so it's not an instrumental effect. The same we get for sulfur. We could do a 3 isotope plot for sulfur, sulfur 33, sulfur 34, in different molecules. So the black is H2S, the green is SO2, and the blue is CS2. The values are different for the 3 molecules, but the bulk of sulfur is clearly depleted in 33 and in 34. It's non-solar. So that also speaks for a non-homogenized protoplanetary nebula. Because actually, if that would have been well mixed, this should be solar and this should be solar. We detected oxygen, O2. That was not predicted because everybody knows that O2 is very reactive. So in a protoplanetary disk with a lot of age, this has to react to water and has to disappear. We actually have between 3 and 4% relative to water O2, which is a lot. And it follows water very well. The blue curve here is water, the black curve is O2, and then you have CO2, which varies with seasons, as well as CO. That's after the second equinox, at 2.8 AU already. Water was dying off, freezing out, as was O2. O2 is very volatile, but it seems to be very well embedded into the water matrix. So it comes out with water and not by itself. There are 2 explanations for the O2. One is gas phase chemistry in a warm cloud, warm meaning 20 K, which is not very warm. And the other one is radiolysis of icy grains, producing O2. We don't know which one is the correct one. And finally, we have S2. Also, S2 you can do with radiolysis from H2S on dust grains. You cannot do that in the solar nebula. You have to do that before. And S2 has a very short lifetime. At 280 nanometers, it's destroyed within 30 seconds at 1 AU. So even if the solar nebula was opaque, I think it would never have survived in the solar nebula as gas. It had to stay in the ice and never been released in order to be detected now in a comet. So we have several hints for a non-homogenized protoplanetary disk and unprocessed pre-solar material in this comet. And that's a summary of what I already said. So the mixing in the protosolar nebula was probably inefficient, at least where comets were formed. They were probably formed far out, at least 67P. Or then CG has to be an alien, which I don't believe, so. Now to the organic inventory. I'm a physicist, I'm sorry for that. So I always have problems with chemistry, and in order to remember what we have measured, the only thing I knew to do was to build a cometary zoo. So associating molecules with animals. The zoo, of course, is built on water because most of the volatile is water. And that's my zoo. In this zoo, we have the butterflies, which are very volatile molecules, nitrogen, N2, we found N2, oxygen, and carbon monoxide, carbon dioxide. What is white here has been known before in comets. What's brown has been found for the first time in 67P. We have the halogens here, which always remind me of sea water. We have found CH3Cl. You will hear more of that this afternoon. And finally, we were also able to locate the parent of phosphorus, PO, is there. Then we have a lot of sulfur-bearing species. So the stinky ones here. And this smells of swamp. And S2 is bluish, S3 is orange, and S4 is reddish. So this gives you the dart frog here. So we have a lot of organosulfurs, which is also the sign of dust grain chemistry. Then we have the giraffes. These are the long aliphatic carbon chains, up to heptane, probably more, but at least up to heptane we have them. We have the funny animals, alcohols, ethanol you drink, the rest you better don't. So up to pentanol, 5 Cs. We have the exotic birds. These are the molecules I don't know where to put. So they must be exotic. We have some small poisonous stuff here, acetylene, HCN, acetonitrile, and formaldehyde. As I already told you in the beginning, we saw some refractories sputtered by the solar wind. And then we have the aromatics. We have quite a lot of benzene and toluene, but we also see benzoic acid, xylene, and naphthalene. Our mass spec was developed to measure xenon, which is mass 136. We, during the mission, enlarged it to 180. There is not too much up there, and I was not able to locate anthracene, which would be the next one here. We have cyanogen. That's a chameleon because it always disappeared behind something else. And then these molecules smell of horse manure, but there are no horses in a zoo, but there are zebras. And of course that's important here because lions feed on zebras. And with methylamine and CO2 you can actually get glycine. And we found glycine. And the newest animal here, well, what you see here is a whale. You will hear about the whale in the next talk. The newest addition to my zoo is the bear. I'm from Bern, and the animal of Bern is the bear. And it's black, because that's probably what makes a comet so black. We have a lot of unsaturated carbon chains and rings. And this we found actually very late in the mission, about 3 weeks before the mission ended. Our instrument got a big piece of comet into its ion source. The ion source was at 1 degree Celsius at that time, and this material started to sublimate in the ion source. And that's the result. With our mass spec, we can sort them according to their functional groups. So these are all CHs, then CHO, CHN, CHS. What's interesting here is that the amount of CH is very similar to the amount of CHO. So if you have only CH or if you have CH with an O, that's about the same amount. But you also see it goes down with carbons, as you expect, but not for the CH. It levels off here. And that's most probably because of the aromatic we have starting at C6. Cn is depleted as the comet is depleted in N anyhow, so we have relatively little CHN. We have quite a lot of CHSs here, and it's also decreasing as expected with carbon. Then we have the O2, so 2 O's, it's quite abundant in the O2. We have the OS, the ON, and finally the S2. I didn't really find molecule CN2. It's probably not below our limit. So this gives you a huge amount of organics. And I estimate it's roughly 1% relative to water, which is quite a lot. We tried to fit that. Our instrument fragments molecules which enter the ion source. They are hit by electrons to ionize them, and that fragments. We know the fragmentation patterns, and we tried to fit the CHs with all the saturated aliphatic and aromatic molecules we saw. So we have the parents, and then we just put in the fragments. And as you see, we can explain the C2 here. We can explain most of the C, but not all. And as this is a logarithmic scale, we can explain only 1/3 of the carbon. 2/3 we don't know where it comes from. And you see here many white lines, so the colored lines we can explain, but what is white, it's not in the fragmentation of these molecules here. So I think it has to be unsaturated fragments in the comet itself. And a lot of them. Biomarkers. It's probably also interesting for astrobiology. So we have several biomarkers here in the comet. I didn't see one single animal on this comet. So the question is really, are these biomarkers, or do we have to revise our list of biomarkers? It's a big question mark. If you have them in the comet, you probably have them in the pre-stellar stage as well, and they are universal, not bound to any animals or plants, whatever. So did comets deliver material to the Earth, and if so, how much? We can get this value from the xenon. from the amount of xenon we have. We know today, that's the xenon as of today, it's cometary xenon versus cometary water. We know we need 22% of cometary xenon, and that gives you this line here, and that would mean we get below 0.1% of the water from comets. But the Earth used to have much more xenon. It lost the xenon. It must have lost the xenon, as we see in the fractionation. So that's probably the initial atmospheric xenon, and if you take this line, then you get roughly 2% of water coming from comets. Of course, this does not change your D over H. 2% is not enough. It will not change. But then you can just calculate. The Earth is 10 to the 24 kilograms. Surface water is 1 per mil. And by comets, you deliver 1% of that. So that's 10 to the 19 kilograms. If we assume 1% of volatile and semi-volatile organics, then we get to the 10 to the 17 kilograms of organics coming to the Earth by comets. And for astrobiology, this may be important because they come in chunks, in big chunks. So for this, you need roughly 10 to the 5 comets hitting the Earth. Each time you get 10 to the 12, 10 to the 13 kilograms of organics in more or less one spot. So maybe that gives you the concentration needed to spark life at one time. And then there is much more organics, and you will hear that in the next talk in the refractories in the comet, and that gives you then much more than from the volatiles. So with Rosina and Rosetta, we could actually look at the different stages of solar system formation from the interstellar medium through molecular cloud, star formation, protoplanetary nebula, to the solar system as of today, and to the probably evolution of life. And these are the institutes who were involved in building this instrument. And of course, it's an ESA mission, and especially ESOC did an excellent job flying this spacecraft around a body like 67P. Thank you very much.
Yes, thank you very much.